Welcome everyone. Let's wait for 5 more minutes to see if other people join. Then we can start. We'll start by 3:05. Okay, welcome everyone. Let's start today's session. So, welcome everyone. Let's start today's session. Channel NPTEL tutorial of microelectronics resistor circuits. Okay. So let's start. So yeah, welcome everyone. This is NOC24 W139 NPTEL tutorial session on microelectronics devices to circuits. The course instructor is Professor Sudhir Dasgupta from IIT Roorkee. He is a renowned professor in the clean domain in India. I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar. So as you know that we go live every week from 3 to 5. So these are some of the prerequisites that it is obvious that you must have tried the assignments and must have gone through the lectures. So okay, let's start. So this is week 8. So we'll be having 4 more regular session and 1 more summary session. So 5 more sessions to follow. So you will be notified accordingly. Okay. So let's begin. Okay. So it is asked that a sinusoidal signal with a period of 1 second, a sinusoidal signal with a period of 1 second has a peak value of this at 25 second and minus 2.5 at zero point 0.7 second. So let us draw the signal. So the your V input in terms of T is given. So 0.25, then we have 0.5, then 0.75, then 1, 1.25. Okay, V in terms of seconds. Okay, so it is given that it's the signal swings between plus 2.5 to minus 2.5 volt. So that means let us say this is 2.5 volt and this is minus 2.5 volt. Okay. So at 0.25 it achieves a value of this, at minus this it achieves a value of this, and it is a periodic signal, so you can safely assume it is a sinusoid. It may not be a sinusoid, but yeah, okay, it is a sinusoid, it is mentioned a sinusoidal signal. So then it becomes obvious that the signal will look something like this. So it will cross a zero here and then it will go like this. It will again get a maxima at here. So this point, okay. So this is the period of the signal. So till this is the period of the signal, okay. Now it is mentioned that this signal has applied at the input of a common drain amplifier, okay. Find out the output value at time instant equal to 2 seconds. Okay. So first thing is common drain amplifier. Okay. We need to understand this. So can any one of you tell me what is a common drain amplifier? Or for that matter, how do you say anything or common gate? We can have common gate, common source, common drain, right? So how to distinguish them and how to if you are asked that it is a common drain or common source, how do you know that?
Input output should be from drains. Common drain means input and output both should be in same.
I think you mean to say something like this. Let's say a device has these terminals, okay? Let's say these 3 terminals, or let's say 4 terminals. This is a MOSFET. Let's say this is your drain, this is your gate, this is your source, this is your body, okay? So let's say the MOSFET is N type. So let's say it is permanently grounded. The body is permanently grounded. This you must have studied in your twin tap process, right? So can you tell me between which 2 terminals I should have the input? for a common drain? So common drain means this will be your one case, this will be your another case. So let's say this is your input and this is your output. Okay. So Ravindran, you want to say anything?
Yeah, the input is at the gate.
Input is at the gate. So why cannot be the input at the source? From the definition, it is like that
Yeah,
your drain has to be the common terminal, right? This has to be the
yeah,
common
yeah.
terminal between input and output. Okay.
And output. Yeah,
So we have two other terminals left. That is your this gate and another one is your source. So I can put input at any one of them. Why do we choose gate?
yeah,
Means that is a
the,
question. Why do we
yeah.
choose gate as the input and source as the output?
Gate has a very high
It
impedance. Yeah, infinite.
Yes.
Yeah, kind of impedance.
So if I put any input at source, so my output I cannot get anything out of the gate, right?
Yeah, yeah.
Because there is an insulator
Yes.
prohibiting any conduction.
Yeah,
Okay. So yes, so that is why generally this is how the thing is. So now from this analogy, this black box kind of scenario, you can draw any common source, common drain, any kind of structure. For example, if I draw the common drain equivalent, so this is my NMOS, right? I am not showing the body terminal explicitly. You can show the body terminal. So this will be your gate. So this will be your source and this will be your drain, right? So your input is, let's say, so your this is VDD. Here you have applied your V in and also you have to apply your VGG. So what is your VGG? Okay, we'll come to that. And then you will have your VSS here and you will probe your V output from here. Okay. So let me just write the small signal ones. V in, V out. So is this a common drain amplifier? You are probing your output between this. This is your V out. Okay. This is your V out. And what is your V in? V in is nothing but between these two. Okay. So this is how the large signal scenario is there. Means, by the way, can you guys tell me why these two are important? These three are important. VDD, VGG, and VSS. What are these? These are the DC bias voltage, right?
yeah,
yes, sir.
So we need to first determine in which region our device device has to operate in linear, in saturation, in strong inversion. So the voltage applied at the gate with respect to source determines that whether my device is in weak inverse depletion or in inversion. Okay, in inversion my device is turned on, and if my device is in depletion, that means my VGS is less than threshold voltage, that is the DC voltage. Remember that. That VGS, if less than threshold voltage, that means my device is turned off or in subthreshold region. Okay. And similarly, based on the bias applied at the drain side, we will know that whether my device is operating at the linear region or at the saturation region. Okay. So this determines your Q point or quiescent point. Okay. Or we call it also bias point. And then what we are doing, we are applying the small signal voltages which we want to amplify. This is V in, V out. These are the small signal input and output voltages. Okay. Now the question is that how does this small signal equivalent look like? So the small signal equivalent. So how do you draw the small signal equivalent? You just make your source. So basically what is happening? Here you are probing your output, right? And ideally what you connect at the source in case of this kind of scenario is a current source. So understand this very carefully. This is your G terminal, this is your S terminal, this is your D terminal. So D terminal is grounded, V terminal, the input is V in and the output is V out. Okay. And this current is your GM times V in minus V out. So please tell me if you have understood this thing, or else I will explain. So what is happening basically in input, your amplifier has a DC voltage. This is your, let's say, this is the voltage axis, V in capital. So this is your VGG, and then on top of that you will have a small V in. This signal is your V in. So, Ravindranath, can you please keep your microphone muted?
Yeah, yeah.
Okay, thank you. So this is your small signal. Similarly, what is happening at the drain? At the drain, you have a fixed signal, that is your VDD. Similarly, at output, you will have a certain DC level, and on top of that, you will have your amplified V out. Okay. So in a small signal sense, we say that it is equivalent to, so basically this thing is equivalent to considering my input signal swing around 0 volt, in this is in small signal sense. So what is happening? Your DC bias is not changing. Okay. The ripple around the DC bias or the small signal is what is getting actually amplified. Okay. So we are concerned about that only. So we can do what? We can just shift the DC level to 0 and assume that my DC signals wherever are present is grounded, and that is because it is a voltage source. Okay. So if I say it more clearly, so ideally what was there? This was your VDD. Then this was your V in, and then this was your VGG. I am just ignoring the coupling capacitances for this time being, that you can use. And then you have a current source at the source, and then you have a, you are probing your output at this place. Okay. So now what we do? We just null it. Nulling voltage source means you just short it. Similarly, this DC also gets nulled. And what about this current source? Current source nulling means open circuit. This is short circuit. Again, this is short circuit. So your small signal equivalent becomes this becomes grounded, this becomes your V out, and this is your V in. Okay. And what you have been studied so far, how to analyze the small signal equivalent circuit for a MOSFET is something like this. So this is your one terminal, this is your another terminal, this is your, let's say this is your gate, this is your drain, and this is your source. Okay. So far what you have studied, that the voltage source between the voltage difference, let's say this is your V in, and you are probing your V out from here. Okay. So this will be your V in minus V out, and this translates to a dependent current source, that will be your GM times this VGS, which is V in minus V out, and you will have a output resistance RDS connected to this, and this terminal of your drain is grounded. Okay. This is how you have studied the small signal analysis so far, but it takes quite a little bit of time to draw this equivalent circuit and then analyze. So what we'll do, we'll use a simplified approach. We'll keep our symbols same and just assume that this is my V in, this will be grounded, and there is a RDS connected here, and we'll mark that this will be my, this current will be my GM times V in minus V out. Okay. So this is a simplified symbolic representation of the small signal circuit. So this and this are equivalent. Okay. Another way to represent the same thing is that this is small signal equivalent 1, small signal equivalent 2, and another way, this is minus GM, this is your V in, and this is your, okay, I'll introduce this in case of common source amplifiers. Okay, not in this case. For the time being, you just understand this much. So now analyzing the common drain amplifier, let us take a common drain amplifier. I can take any configuration, but let me choose this one. So this is your VDD. There, let's say there is a resistance RS. This is your V out, and here you are applying your V in, and also you will have your VG. Let's say VGG. Okay. So your small signal equivalent will be a resistance RS, V out, V in, and this will be grounded. Okay. And let's assume for simplification of analysis that RDS tends to infinity. That means this resistance is almost infinity. So We can assume it to be an open circuit. Okay. So now what is the current flowing in this case? Can anyone tell me? The current flowing has to be Gm times VGS, this difference of this voltage. So what, this is my source terminal, this is gate terminal, this is drain terminal. So what is my VGS? VGS is nothing but VG, that is V in minus V out. Okay. So is that clear?
Yes, sir.
So now can you tell me, please tell me the KCL at this node. So applying KCL at the source node. Can anyone tell me the equation? KCL is current balance, right? Whatever current is coming in, that should go out. So what is the current coming into this node?
GM times V in minus V out.
Gm times V in minus V out. And what is the current going out of this node? This current is going out, right? What is this current? This is ground. So what is this current? How do you find out a current in a resistor? You should use Ohm's law, right? It will be nothing but your V out minus ground over RS, isn't it? Anyone?
Yes, sir.
So what are we having? GMRS times V in minus V out is equal to your V out. Okay. So GMRS times V in is equal to your V out times 1 plus GM time RS. So your V out over V in, or that is the gain, voltage gain, is what? Is your GM times RS over 1 plus GMRS. So what do you think the value of GMRS with respect to 1? Is it greater, lesser? What is your take on that?
Greater.
It is generally much greater than 1, okay? So what can you conclude? Your AV for a common drain amplifier will always be very much equal to 1. Actually, it is a little lesser than 1. But we can almost approximate it as unity gain. So what kind of device is this? Basically, this device, if I just copy it, this device is equivalent to an amplifier with a gain of 1. So what does it called, by the way?
Buffer.
It is called a voltage buffer. Okay. You remember in the first session I have discussed about the importance of voltage buffers in the circuit analysis. Whenever you need to isolate two cascade stages,
Impedance matching.
exactly. Whenever you need to isolate two cascade stages, you use a unity gain buffer at the inside. Why? Because ultimately it is an amplifier, right? It is seeing high input resistance and low output impedance. Okay. So this is a voltage buffer. So now tell me, this was my sinusoidal signal. So this was my input signal. And you want to find out on the output at, let's say this is your 0.25, zero point 0.5, 0.75, 1, 1.25, 1.5, 1.75 and 2. So this is your V out. So it will be your 2.5 line and it will be your minus 2.5 line. So your output waveform will be, it will start at this point, then at this point it is negative, again at this point it is positive, again at this point it is negative. So at 2 second, my output is how much? Output will be equal to 0. Okay. So my V out at t equal to 2 second is equal to 0. So this is what was asked in the question. So what are the concepts involved in this question which we need to remember and understand? First, we need to understand the concept of sinusoidal signal. How does it look like? You should be familiar. I know you are familiar, but again, it doesn't harm you to understand how the sinusoidal signal, if the peaks and valleys are given or the maxima and minima are given. So you should be able to draw that and you should be able to understand what is the period of the signal. Okay. And then you need to understand what is the common mode operation mean. Okay. What does the common mode operation mean? And how you can draw any of the common gate, common source or common drain amplifier symbols. For just you have to understand this much, then it will be easier for you to understand. Then third concept involved is the biasing you need to understand, and how does from the biasing we go to the small signal circuits. Okay. And then I have given you a simplified way to solve the circuit. You do not need to draw this every time. You do not need to draw the current sources and all. If you understand the concepts, then you will be able to solve using the conventional symbols itself. Okay. Just you need to be sure that in small signal your voltage sources nulling becomes grounded or the short circuit, and your current sources become open circuit. Okay. So by the way, can you tell me how did you have noticed that I have used a current source here, common drain, and here I have used RS. So can anyone tell me that why was I able to do that? these two represent the same common drain amplifier. The question is, what is a current source? This is an ideal current source, okay? Let's say I0. And how does a practical current source look like? Practical current source has a parallel impedance along with it, right? So when you open circuit this thing, this RP remains, okay? Similarly, when you have a voltage source, you have a series resistance with it. A practical voltage source has a series resistance along with it in series. This much you are familiar, right?
Yes, sir.
So that is how these two circuits, this one and this one, shows you the similar kind of behavior, okay?
Okay.
Because if you consider a practical current source, let's say you will have a RSR. This RS is coming into picture after you go to the small signal analysis and open the ideal current source. So that is all about this problem. Let's move on to the next one. Okay, for fast operation of MOSFET circuit, the MOSFET requires. So what is your take on that? So what does fast operation mean, by the way?
Transmission times should be 0.
Transmission time should be 0. Okay, let me just tell you this. So let's say this is a common source amplifier. This is your V in. This is your VDD. Let's say this is your RD, and this is your V out. Okay. So how do you say that? By the way, did I use correct symbols? Yeah. So how means fast means what? If you apply a signal here, the output should swing simultaneously, right? That means let's say this is time axis. So this much you have understood, right? Fast means it has to do with time. Okay, you need to have lesser amount, you need to require lesser amount of time. The lesser amount of time required for input to travel to the output, the circuit will be more faster or more faster, right? So let's say this is your input signal. Let's say you have certain gain, but your output will have a, let's say your output is having a lag. Okay, so this means that your circuit is not, its circuit is lagged, right? That means circuit has a certain amount of delay. As soon as you start changing the input, your output is not has not started to change. So from the basic circuit understanding point of view, can you tell me what element caused this delay?
Some storage is there like capacitor.
Exactly, absolutely correct. So fast operation means it has to do with some capacitance, right? To be very honest, in your circuit has many capacitances. This CGD, it will have this CGS, then it will have your CDS, then it will have the next stage will be having some gate, right? Gate of some different transistor. So it will have some kind of load capacitance. We can model it in the digital circuits. We have analyzed this. So passing of a signal through this capacitive coupling, we call this capacitive coupling, requires charging of these capacitances, and that charging of these capacitances are not instantaneous. For example, if you have this kind of input signal with an RC network, so it will start to lag, and then maybe after 4 tau time constant or 5 tau, you will get your desired around 98% of that signal. Okay, then you can approximately assume that your signal has traveled exactly. But this 4 tau and 5 tau, these are the elements which is causing delay. So this tau are what? R equivalent times capacitance, total C equivalent. So this capacitive coupling you always have to remember in mind. Okay. Now the question is that, do you think that your higher current gives you better less delay, or lower current gives you less delay? This we have discussed in case of digital circuit. So I is what? Basically I is your Q by time, right? So your time will be lesser when I will be higher, provided Q is determined by your CV. This is the zeroth order approximation of the concept. So if you have higher amount of current, to get the same charge, I need lesser amount of time, or my circuit will be faster. So if I can have, you remember that we had discussed in case of digital our IDVG, that I want my ion to be higher, right? For faster operation of the circuits. So
Yes,
this is
sir.
the same case. This can be translated into the analog domain very easily. So basically, what is your I? Let's say in saturation, what is your I? Half mu n C ox W by L VGS minus VTH square. Let us assume the channel length modulation. Let us ignore the channel length modulation. So what will be your GM? GM is by definition DID by DVG. Okay. So that is what? That is your mu n C ox W by L VGS minus VTH. Okay. So now can I write it this way? Half mu n C ox W by L VGS minus VTH whole square divide by half times VGS minus VTH. So this is what? This is your ID. So can I write my GM like this?
Yes, sir.
Another way you can write GM. So let's say this is what when your this is called V over drive is constant. Okay. So in any case, you will see that your GM increases with ion increases. So higher GM will give you faster operation of MOSFETs. Okay. And let me tell you another way. So this is one way to understand. Okay. That your higher GM will help you to achieve faster operation. Another way, if you let's say this is your AV voltage gain in dB scale and this is your omega, and let's say you have something like this. Can you recognize this plot? What plot is this? This is a Bode plot, right?
Yes, sir.
So for a common source amplifier, so this is your omega low and this is your omega high, the region at which this is 3 dB lower. So can you guys tell me what does this point, which determines this point? This is generally determined by your coupling capacitances. Okay. Basically, what is happening? This is your RD, this is your VDD. Then you will have your V signal. This is your C1, this is your C2, let's say, and this is how your circuit is. And there are other capacitances, CGS, CGD. Okay, so this is called a pole. This is basically a zero, not a pole. This is basically a pole, not a zero. This is a pole. So this is, let's say, called P1. Let's call this P2. So this is determined by, it will be in the form of some G over your C coupling, and this will be in the form of GM over your capacitances, your CGD, mainly dominated by CGD times your 1 minus A plus CGS, let's say. For the timing, you understand it and just take the words in this fashion, just to understand the concept what I am going to convey to you now. So this is called what?
Bandwidth.
So what does bandwidth signify basically?
uh, by this much amount. Further, beyond this bandwidth, signal will attenuate. Clamping is there
So,
after that bandwidth.
okay. So this range of frequency, so this range of frequencies of what? This frequency is what frequency actually? Which frequency we are talking about?
3 dB bandwidth.
Sorry?
I don't know.
No, no. This omega is omega of what?
of the input signal.
So of the input signal, A sine omega t. Okay. So your output will also be in the form of some, let's say, C times, if you assume only the linear part, C times something sine omega t plus some phi, some phase change may be there. So what it is telling that, let's say I have an amplifier and I am able to amplify this signal. The omega of this is omega, this is, it lies between omega and omega L and omega H. Okay, the frequency of this signal, input signal, lies between omega L and omega H. So within this range of frequency, or within this range of input signals frequency of the input signal, I will get an amplification, or my output signal will be an amplified version. Okay, the desired amplification will be there. And what is that amplification? This is the, this gain, basically this gain, this value is the value, because this is ultimately what, this is your V out by V in. So your signal will be amplified by this amount. Okay, now if you start to increase the frequency of the signal, let's say your input signal is like this. Okay, so you will be, means basically you are at this range now. So this is your V in. Let's say this is your omega 2, and earlier you were somewhere here, omega 1. So this is your omega 1. Now you are having omega 2 which is greater than omega h. So what is happening? So your output signal gain has reduced. So this value has reduced. That means you will not, you may get a very little gain. Okay. So that is not desired, right? You have designed your amplifier in a way that you should be able to hear the sound, or maybe something else, some different signal. The amplified version should be what you have desired or designed the circuit for. But now you are not getting that signal. Not that much of amplification. This is why, because your output is crossing the band, out frequency of the input is crossing the upper limit of the bandwidth of your amplifier. Okay, so if I can push my WH beyond this, then I can say that this is also acceptable frequency for me. In other words, if my output curve is something like this and my omega h2 is somewhere here, then this frequency is falling at the mid band range and my gain is getting intact. Fine. So how do you increase this omega h? You increase your omega h by increasing gm, because your C's will remain constant. So you increase your gm. So in other words, increasing gm means you are now able to cater higher frequencies at the input for which you will get the desired amplification. Is the point clear?
Sir, but GM is fixed for a device, na? It is a
No,
device
no,
parameter.
no, GM is
We
not a
obtained
device
from the
parameter.
graph by GM is the slope of the flat band.
GM is the slope of the, no, no. See, in a real device, how does your IV look like? This is your IDVG, right? Your IDVG, if you see in linear scale, it will be something like this. This is your linear operation. This is your saturation operation. Okay. So if you plot your GM or just the derivative of the signal, you will see something like this. Okay. This is your linear. This is your saturation. So your GM is not ever constant. You see, as you change your bias, your GM changes. You can change your GM by changing W by L also. You can change your GM by mobility engineering also, strain engineering we call it. You can change your GM by using high K dielectric also, or thinning of your oxide layer also. You understand?
Yes, sir.
So GM is not a fixed parameter. GM is fixed when you calculate the large signal analysis for a given set of parameters and voltages. That is when you solve the problem. But what I am telling you now is the designing perspective. That suppose you have made an amplifier, okay? You have designed an amplifier, but now you want to improve the bandwidth of that. How can you do that? You can improve your GM. How can you improve your GM? You can improve your GM by tinkering with these parameters. Okay, so that you can apply a higher frequency signal at the input. So that is also in a sense that increasing GM gives you a faster operation. Faster means high frequency signal you can accommodate so that your gain is not compromised.
Sir,
Yeah.
except VGS, all the parameters are already fixed.
No, no,
Whether it is
that you design, right? Your process does see how the design flow happens. Okay. So you're deviating, but I think it should be so how a analog IC design happens for, let's say you want to design an amplifier, okay? So what are the steps? First step, you are given that, let's say you need to have a, 60 dB gain, okay, over a and a bandwidth of, let's say, 2 gigahertz, okay. These are the specifications you are given, specs you need to meet, okay. And let's say your phase margin has to be around 70 degree, okay. Just listen to the terms. I will not explain what phase margin is. Phase margin you can calculate easily if you have studied control systems. This is the amplitude plot of the Bode plot, and if you see the phase plot of the Bode plot, then you can easily get the phase margin, okay. And that is related to somewhat stability of your circuit, okay. So say this is given to you, to the analog designer. So what he'll do, he'll, a foundry or the fabrication unit, let's say TSMC or Global Foundries, provide them a certain tool that is called PDK or Process Design Kit, which specifies all, let's say for a 65 nanometer CMOS technology, okay. It has all the parameters fixed except your W and L that the analog designer can choose, okay. So by changing and optimizing the W by L and the architecture of the amplifiers, you have studied multiple architectures, right? Cascade, cascode, then folded cascode. There are so many types of amplifier topologies, which gives you multiple benefits. Some gives you more stability, some gives you more signal swing at the output. So suppose you have come up with a design. where you have fixed your WL and amplifier topology. Then you send it back to the fabrication unit, and then you get your physical amplifier. Okay, so when you solve the problems in the questions or in exams, that is kind of analysis of how to solve the or numerically compute the values of multiple parameters. That will help you in future in this stage of analog IC design. Okay, at this stage you will need to require to suppose this problem you need to understand, right, that you need a larger GM to push your pole to at a higher frequency. So that you will play during this phase in your future endeavors. Okay, so from foundry point of view, this has this has fixed TOX, fixed mobility and everything. But then again, why am I choosing 65? You can ask them for 45 nanometer also. So that is up to the designer, which technology he wants to go. That is also a choice which the designer has to make, depending upon what is the constraint of his and what are the specs he needs to meet and what are the funding or budget he or she has. Okay. So this is the flow. You start with the spec, then you are given a certain constraints called PDK, then you start to design, then you draw the layouts, and then you go for the multiple verification layers, and then you send it to the fabrication unit. They fabricate it, send you back, you do the testing, and then you are done, and then you ship it to the companies. Okay, does that answer your question?
Yes, sir.
Okay, so yeah, so basically fast operation I wanted to just mention, it is related with the capacitances. Okay, and your GM helps you to increase your ID, or in other sense charge the parasitic or the load capacitance at a faster rate if you have a higher GM. Okay, understand this much. Okay, so let's move on to the next problem. Okay, so calculate the small signal gain of the given circuit. Okay, so what do we need to have to calculate the small signal gain? Let's say I first draw the small signal equivalent of the circuit. Okay, so how will it look like? It will look like something like this. Then I have V in here, I have RD here, and what will I do to this VDD? In a small signal, what will I do this VDD?
Ground.
I will just ground it, and here I am taking my output V out. Okay, so in a small signal equivalent, what is the first thing you need to do? You need to get this current. This current will be GM time V in minus 0, because this is the source voltage, this is the difference between gate and source. So it will be simply GM V in. So what is unknown to me, or let's say if I want to find out the gain, so AV will be what? V out over V in. right? So what is V out? Can you quickly tell me? From this current, this is an open circuit, right? So no current flows here. So this GMV in has to flow through this. So this will be minus V out over RD, right?
Yes, sir.
So what is your, and what is your V out? V out is, so your V out over RD is equal to GM times V in. So your V out is what? Minus GM RD times V in. So minus GM RD times V in. V in cancels. So minus GM times RD. Okay. RD is given. What is RD? RD is given as 1 kilo ohm. So, but what is not known to me? GM is not known, right? So, how do you find your GM?
ID by
Anyone?
VG minus VTH.
So, basically, your ID is equal to half mu n
Simply
Cox W by L VGS minus VTH whole square times 1 plus lambda VDS, right?
lambda 0.
So, lambda is 0. So, this will go away. So, ID you do not have, right? So, you have half mu n Cox W by L VGS minus VTH whole square. So dID by dVG is equal to what? Mu n Cox W by L VGS minus VTH. So you, okay, ID is given, right? So this is your GM. GM is mu n Cox W by L VGS minus VTH. So what I'll do? This is equation 1, this is equation 2. I'll just do my GM by ID. So this mu n Cox W by L VGS minus VTH, and in this case it is half mu n Cox W by L VGS minus VTH whole square. So this gets cancelled, this entire stuff gets cancelled. So GM will be your nothing but 2ID by VGS minus VTH. So what is your ID? Your 2 times 2 milliampere over your VGS, your VTH is given, VGS minus VTH you need to find out, right? So VGS minus VTH, how can you find out? From this equation, ID is equal to 2 milliampere, half your mu n Cox, mu n Cox is given as, mu n Cox is given as 100 into 10 raised to minus 6, 100 into 10 raised to minus 6 times your W by L is given as 0.18 times your VGS minus VTH. So your VGS minus VTH will be, so this is 1000, this and this will get cancelled. So your, this will be how much? 0.18 times 2 times So it will be around 0.72. Please correct me if I am doing the calculation wrong. So this is 100 10 raised to minus 6. It is 0.18. Okay, VGS minus VTH is this. So 0.72. So that will be 4 divided by 0.72. That is your 5.5 millisiemens. Okay. So 2 milli, this is VGS minus VTH. So 4 divide, let me do it freshly. Okay, so we had this equation. From equation 1, we had ID is equal to half mu n Cox W by L VGS minus VTH whole square. So we had 2 milliampere, then we had half, then we had mu n Cox, we had 100 into 10 raised to minus 6, we had 10 over 0.18, and then we had VGS minus VTH whole square. Okay, so this gets cancelled. So 0.72 is equal to VGS minus VTH whole square. So VGS minus VTH is your square root of 0.72. It is your 0.849. So this will be 0.849. So that is 4 divide answer is your 4.71 millisiemens. Okay. So now you have your AV is equal to minus GM times RD. GM is 4.71 millisiemens times RD is 1 kilo ohm. So milli 1 will get cancelled. So and Siemens and ohms will get cancelled. So it will be minus 4.71. Okay. So your gain will be minus 4.71. So did you observe one thing? Your GM is depending upon the bias you have applied. Okay. The large signal parameters. Can you tell me why? So GM we find out from large signal analysis. Can you tell me why? Let's say this is ID, this is VG, okay? And let's say this is how your plot is. What is GM?
Slope.
So this is one point. Let's say this is VG1 and this is ID1. And let's say this is another point, VG2 and ID2. So what do you think? The slope at this point and the slope at this point, are they same?
So they are different.
Why they are different?
First, the curve is changing its slope.
So
Both
that
are
means you will have a GM1 here and GM2 here, two different GMs, right? So
right.
GM depends on at which point you are biasing your circuit. This is one bias point, let's say bias 1. This is another bias point. And why does it happen such way? For example, let's consider a MOSFET, okay? This is N plus, N plus. Let's say this is drain, this is source, this is gate, and this is body, okay? So let me just copy this.
It is due to different mode,
Exactly, not different mode. Basically,
saturation and triode region and cutoff
uh,
region.
not it is VG, right? You can say that. Let's call me that this is my threshold. You can say that this is subthreshold, and I am keeping my VD constant, right? So there is nothing called saturation and linear. So in this case, both are saturation mode. But in one case, my bias one is at the subthreshold, and another one it is at the inversion, right? So basically, what is happening in one case, I have a majority charge at the depletion charges and very few electrons. In another case, I have depletion charges, but I have a lot of electron. Okay, understood?
Yes, sir.
So if I apply a gate voltage here, if I change the gate voltage in linear fashion, so in this case, my charges will change in a different manner than in this case. Okay, so that
Yes, sir.
is why I will have a different slope. So your transconductance or the slope of any non-linear curve, because if it is a linear curve, I will have a same slope at each point. As it is not a linear curve, I will have a different slope. So my GM is a large signal parameter, or in other words, GM is a small signal parameter derived from large signal analysis. That is more correct. Okay.
Okay.
So please remember that whenever these kind of circuits are given, so I have deliberately did this way. So this step you should do first, the large signal analysis, or this is called sometimes the DC analysis, and then you go to small signal analysis. If you start with this, let's say in your gate exam or some other different, you will lose more time. Okay, so it is better to start with the DC analysis, find out the GM and other required parameters, and then go for the small signal analysis. That is how it has been taught in all the reference books also. Okay.
Okay.
Okay, so let's move on. Okay, so in this case, GM1 is given as 20 millisiemens. VTH is given. By the way, VTH is a large signal parameter or a small signal parameter?
Okay.
Anyone? Yes, VTH is a DC parameter or an AC parameter?
It's a DC parameter.
Yes, VTH is a DC parameter because it depends on the bias points only. And what is the definition of VTH? Even not in bias point. Okay, I think I did not discuss the moderate inversion. So VTH even does not depend on your large signal bias. It simply depends on your VFB plus your 2 phi f plus your gamma times square root of 2 phi f, where your phi f is defined as the bulk potential, that is the thermal voltage, log of the doping of the body over the intrinsic carrier concentration, right? And your VFB has two component we have studied in MOSCAP portion, minus oxide fixed charges over capacitance. Okay. So anyway, just to make sure that you keep track what is going on, so I keep repeating these things over and over again. So this is your RG, this is your RD, this is your VDD, okay, and this is your M1. I think this is how it is given. Okay. So how can you solve this circuit? Or how do you solve this circuit? What is given to us? What is the okay? So let us solve this way. ID is flowing here, is flowing here. Is this statement true? Is ID flowing only at the vertical branch and no current is flowing in this branch?
Sir, at
Yes.
Yeah.
last gate is open circuit, so ID will flow in that branch only.
So the blue part is you have understood, right? Why I have drawn that
Yes.
ID? Okay.
Yes, sir.
Yes.
So now your ID is what? Half mu n C ox W over L VGS minus VTH whole square. Okay.
Yes, sir.
If you ignore the uh,
Lambda.
channel length modulation. So what is your GM? GM is basically mu n C ox W over L VGS minus VTH. Okay.
Yes, sir.
GM is given, right? GM is given as
20
20 millisiemens. So mu n C ox W by L times VGS minus VTH, you know. So now 10 raised to minus 3 equal to mu n C ox W over L. This is what your VGS minus VTH. Let's say VGS minus VTH whole square, and let's say half, and in this case half VGS minus VTH. So this becomes your ID VGS minus VTH. Okay. So is your ID given? ID is given as 1 milliampere. So VGS minus VTH is what? 2 into 10 raised to minus 3 over 20 into 10 raised to minus 3. That is equal to what? It is 1 milliampere and 20 millisiemens is given. So it is 0.1. So VGS is what? VTH is given as 0.4 volt. So VGS is 0.5 volt. Is that clear?
Yes, sir.
So what is your VS? VS is 0 volt. So VG will be 0.5 volt.
Yes, sir.
What about this voltage?
Okay.
This one, let's say this is VD. What is VD? There is a resistance RG. One point is connected to zero point 0.5 volt. There is no current flowing. So what should be the voltage at the other point for no current to flow? Because RG is not zero, right? R,
0.5.
Yeah.
so this has to be 0.5 volt.
Yes, sir.
So now what? Your ID is equal to what? From this branch, you can write VDD minus VD over RD.
Yes, sir.
RD is given as 1 milliampere. VDD is given as 1.8 volt minus zero point 0.5 volt over RD. So your RD becomes 1.3 kilo ohm. Did you get it?
Yes, sir.
Okay. So that's fine then. Okay. So yeah, the MOSFET gate to source capacitance in saturation regime can be given as this. Neglect the overlap capacitances. So if you know the structure of the MOSFET, let's say this is N plus, this is N plus, this is P. Okay. So tell me one thing. This is, let's say, VDS. So when VDS equal to 0, how will my charges look like? Is it okay?
Yes, sir.
When VDS equal to 0,
Yes, sir.
and what about now?
Uh, I, it will. electron will, and it's
In
like saturation kind and pinch off,
yes.
right?
So why does pinch off happen basically?
Because the channel VC is changing. VC is compared to VGS. When we compare VC to
So
VGS,
at this point, what is the voltage? You have V, let's say you are applying VDD here also, okay? So at this point, what is the voltage? VDD.
yes, sir.
At this point, drain end, what is the voltage? It is zero, right? Because drain is also at VDD, gate is also at VDD.
Yes, sir.
So your channel will be something like this. Okay? It will be like a trapezoidal.
Yes, sir.
Another thing which is don't often mentioned, that these depletion charges at the drain end. So basically earlier it was the depletion boundary, right? Now the depletion boundary will be something like this. Can you tell me why?
Because here PN junction,
Yeah, yeah, go on. The
uh,
drain body PN junction is reverse biased, okay?
yes, sir.
So as a result, the depletion width increases. So
Yes, sir.
these two phenomena you will observe. Fine.
Yes, sir.
So there is something called, okay, no, just not let me go it right away. I'll just explain something more. Okay. So again, now your QG is equal to QS plus QB plus QI. This is your gate charge. This is your depletion charge. This is your inversion charge. Okay.
Yes, sir.
So the signs are opposite. So basically, if you draw the charges with respect to VG, so this is, let's say, VFB point, and this is QG, let's say. So you will have something like this. This, then this, then this. Okay. So this region is your accumulation, this region is your depletion, and this region is your inversion. So if you take your CGG with respect to VG, so it will be having a slope of this,
And then lower.
then it will go low, and then it will again come back to this. Okay.
Yes, sir.
So this is basically, now from this equation, dqg by dvg is equal to dqb by dvg plus dqi by dvg. Okay. So in saturation region or in strong inversion, let's say, first we'll discuss strong inversion, then we'll go to saturation. So in strong inversion region, your QB doesn't change with VG. It almost goes to zero.
Yes, sir.
Majority contributor is your inversion charge.
Yes, sir.
So your CGG is almost equal to your, or let us not go into strong inversion explicitly. So let me just do it in this way. CGG will be is your CGB plus CGI, let's say. But this charge, this inversion charge QI is this one. Okay, this is your QI. So QI has to be, some portion of the QI has to be assigned to source, and some portion of the QI has to be assigned to the drain. Okay,
Okay.
so this is called, QI is basically QS plus QD. This is called charge partitioning. Partition the inversion charge among source and drain terminal. Okay. So now what is happening? In case of linear region, or let's say when my VDD is almost equal to 0, VDS is almost equal to 0. So this is like a rectangle, the inversion charge profile.
Yes, sir.
So I can assign 50% to source
Yes, sir.
and 50% to drain, right?
Yes, sir.
At pinch of, or let's say beyond pinch of saturation, when VDS, let's say equal to VDD, how much should I assign to source and how much should I assign to drain?
More to source, less to drain.
More to source, less to drain. So there are multiple methods what scientists have proposed in the history. One is your 100% to source, 0% to drain. Another one proposed 60% to source, 40% to drain. And there is another theory which is called Ward-Dutton charge partitioning. Okay, what does it do? It approximate the thing as linear function and then partition the entire thing linearly from source to drain. It is not a exact function, but it is through a linear extrapolation from source to drain. Okay, so I just want you to get familiarized with this term, that there is something called Ward-Dutton charge partitioning scheme. What is the most popular one, which is even used in digital parlance also, is this 60-40. Okay,
Yes, sir.
so in case of strong inversion, what is this value of this capacitance, by the way? What is the value of this capacitance? Cox times WL. WL is the area and Cox is the oxide per unit capacity per unit area, oxide capacitance per unit area.
Yes, sir.
So in this place, my CGB is 0, as we have earlier discussed.
Yes, sir.
So, and my CGG is WL Cox, and CGI will have two component, dqs by dvg plus dqd by dvg. So it is assigned 60% and it is assigned 40%. Okay, so your cgs will be 2 over 3 WLCox, and your CGD will be 1 over 3 WLCox. Okay, so this is So the concepts involved are the profile with has to do with the profile of inversion layer charges, and then how you define your capacitances, and then how you partition your charges. So this concept is very important for the first hand calculation of the your CGS and CGD, which plays a critical role determining your cutoff frequencies and your delays in your digital circuits. Okay,
Okay.
but if you plot the things in spice, spice will give you exact CGS and CGD, and it is based on Watt Dutton charge partitioning. Okay, so by the way, do you guys know about spice?
यस सर सुने यूज किए थे मगर भूल गए सारा कुछ.
Okay, no worries. You LT spice you should have used or
यस सर.
micro cap, right?
यस सर.
Okay. So yeah, find the bandwidth of the given amplifier. The device's parameters are GM, RDS. Okay. So how do you find out the bandwidth of certain circuits? So again, bandwidth is related to these two values, determining these two values. Okay. The Bode plot may not look like this. I will show you in a short time. This omega L and omega H, basically you need to take into account the capacitances. Okay. So how do we solve for bandwidth kind of problems? Okay. So what are the capacitances we have? This is my CGD and this is my CGS. These two are given in the question. Okay. CGD and CGS. GM is given, then RDS is given. Okay. So you need to find out the bandwidth. So how will you do that? Again, we go to the small signal representation. Let me show you a different kind of small signal representation. What is this? Have you seen this kind of symbol anywhere before? Anyone?
No.
So if you apply V in here, what this tells you that you have a current of GMV in at the input, at the output coming in. Okay. So this is nothing but a small signal, another kind of small signal representation of the circuit. Okay. So this is called basically open transconductance amplifier or your OTA. This is how actually your MOSFET behaves, right? This is your VG and this is your ID. MOSFET in a saturation region under strong inversion condition acts like nothing but a current control, voltage controlled current source. This is the same stuff which you draw like this. So this is your GM V in and this is your V in. Okay. I have just replaced this entire thing and gave you this symbol. So what is the current here? Current coming in is GMV in, right? Now can you correlate the two things? This you know, right? I assume.
Yes, sir.
So this and this are the same thing, just a way to represent, because why I am introducing these things to you, whenever you will do your higher studies or go for further circuit courses, no, you will start to encounter this kind of symbols. So you should not get scared at that point. Okay. These are the very simple things and same things you already know, but just a different convention to represent. This is how the circuit designers use it. So you understood, right? Why I have written like this?
Yes, sir. RDS, if RDS there.
If RDS there, good question, very good question. If there is RDS,
No, sir,
so
not in that.
yeah, I
Wave
will
of,
just show. So I will just simply connect here RDS. Now is it okay?
sir, there that is in parallel, and there you connected in ground.
So your source is grounded, right?
In general, sir, if not grounded.
In
If
general, actually you will have a, this OTA will have a two terminals, okay? It will be something like this. This is minus, this is plus, this is GM, this will be your gate terminal, this will be source terminal, and this is your drain terminal. So you connect it like this if you have certain source voltage.
okay,
Okay?
yes,
Wait, just let me keep it for the record. Okay. So this is the symbol which we are going to use for the convenience, for our convenience. Okay. You will see why we are using this symbol. Okay. So now I want to write the small signal equivalent. So what do I have? I have a minus GM OTA here. Then I have a RDS here. And what about RD? Can I write RD in parallel?
yes, sir.
And my R signal at series. So this will be my V in, this will be my V out. Now I need to have my capacitances, right? So one capacitance which I should have between these two, the CGS. So I will simply put my CGS here. Okay. And what about CGD? CGD will be between these 2 points.
Yes, sir.
Okay.
Okay.
So now let's say I have a system like this. This is my input, this is my output, and I have a load connected across the input and output in kind of a feedback path. Okay. So this can be simplified as So this impedance becomes Z over 1 minus A, and this becomes Z over 1 minus 1 by A. A is the transfer function or the gain of the system. So do you know this? Let's say this is Z1, this is Z2. So Z2 is equal to this, Z1 is equal to this. So do you know how did I do that? This is something called Miller's theorem.
Yes, sir.
You know this,
Capacitance,
right?
capacitance and inductance were distributed in both sides.
No, it has does not have to be capacitances, inductances. It can be done with any kind of load. Okay. Z
Any
is an impedance, right? It has real part and imaginary part also. So it does not have to be capacitance or impedance, inductance. It can be resistance also. Let me tell you a funny story then. Okay. Suppose you have a amplifier gain stage. This is an example. Okay. Let's say you have a gain of 5 and you have a 1 kilo ohm resistance. Okay. So what is the Miller equivalent of this? Just tell me the value of the resistances. Use the same theorem, the same formula as above.
1/4, 1/4.
No, no, calculate it correctly. Tell me which sign.
Sir, 1/1 minus 4, simple. 1/4, 1/4.
1 by 1 minus 4. 1 by that is 1 kilo ohm divided by 4, right? That is what? Minus 250 ohms. And here is how much? 1 by 5. 1 by 5 is what? 0.2.
Yes.
So 1 divided by 5 is 0.2. 1 minus zero point 0.2 is 0.8. So 1 divided 0.8 is 1.25 kilo ohm. So what is your comment on that? You are realizing a negative resistance.
Uh, Power gain is there. Like,
Basically, it is the input resistance, okay? And believe me, this happens in the amplifiers, and this is just for a fun fact for you guys. This causes your stability issue, okay? To mitigate that, you add other resistances to stabilize the circuits, okay? So always remember, whenever you encounter in your circuit design in future, there you are seeing some negative resistances or probing some negative resistances, always remember that there is a gain from that end to the other end. Okay.
okay.
So in amplifiers, in the input side, you get negative resistances because of your Miller effect. So then this CGD, this circuit, I can further draw an equivalent. So this is my CGS. This is my R signal. So I will have a capacitance here. Let's say this is my C1. So I will have this GM. Then I will have RDS. I will have RD. And I will have a C2. So can you quickly tell me the value of C1 and C2? For that, you need to know the gain. You need to know the gain of this block. What is the gain of this block? Because that is where my input and output nodes are, right? What is the gain of this block?
RD parallel R is RDS.
So from this circuit, can you see this is your what? Okay. Before that, just let me tell you this. So this is your GM, right? And there is these two parallel resistances. In DC, my capacitance is open circuit. So this is your V out. This is your V in. So how to see this? This current is your GM times. This current is what? GM times.
And parallel equivalent resistance.
No, this current is GM times V in, right? We have discussed, no?
Yes, sir.
So this current is GM time V in. So this entire current is coming out of this parallel combination. So if current was to come in this direction, this V out will be positive. But in this case, current is going out of this entire resistance and going out. So my V out will be what? Simply the current times this equivalent resistance, and that is my RDS parallel RD. So simply now if you put V out down, your AV will be minus GM times RDS parallel RD. So are you able to visualize this thing? I'm just trying to know that if you can visualize from this topology easily how the gain would be. There is a resistance. If I tell you current coming in is I, so what is V?
V is IR
And if I tell you current is going out is I, what is V?
minus IR.
So now if I give you another resistance, let's say R1, and if I tell you current is going out after this as I, so what will be V?
R1 parallel to R2 minus I.
Times minus of I.
Yes, sir.
So you see, right, this GMV in how I am easily writing it the gain.
Yes, sir.
Okay, so I wanted just to make sure that you visualize this plot correctly. So now what will be my C1 and what will be my C2? So basically what is C1? C1, what is the impedance? Impedance is ultimately 1 over SC1, right?
Yes, sir.
So here impedance is 1 over SC1. So 1 over SC1 is equal to what? 1 over SCGD or the Z in case of this is what? 1 over SCGD, the impedance, that divided by 1 minus the gain. Gain is what? Minus
GM.
GM times RD parallel RDS. Okay.
Yes,
So
sir.
1 over SC1 is equal to what? 1 over SCGD, and this minus minus will cancel. So this 1 minus A was this. So this will be what? 1 plus GM times RD parallel RDS. So your C1 becomes what? CGD times 1 plus GM times RD parallel RDS, and in other case C2 would be similar way CGD times 1 plus 1 over GM parallel RDS. Have you see, did you understood this much?
Yes, sir.
So now you have what? Here C1, C2. C1, C2 you know. C1 is your CGD times, and just let me, for the ease of my calculation, I write it GDS and this I write it GD. Okay.
Yes,
This
sir.
is, and in parallel GDS and RDS, the parallel it will just add up, right?
Yes, sir.
So I can easily write then this will be my 1 plus GM over GD plus GDS. In another case, C2 will be CGD 1 plus GD plus GDS over GM. Okay.
Okay.
Now I want you to find out the transfer function between V out and V in. So for that, what should you do? First consider this is Vx. So you break the problem in two ways, that you do V out by Vx and Vx by V in. Okay.
Yes, sir.
So what is your V out by Vx? Now this everything comes in parallel, right?
Uh, GDS plus GB plus X
Plus
D.
SC2
Yes.
times
And GM.
GM. So it will not be times, it will be GM divided by this.
Yes, sir. GM divided by GM.
Similarly, your what will be Vx by V in? You call it G signal, let's say, for ease of calculation.
G signal by X GS plus XC1
G signal by
plus C1
plus C1
C1.
SC1 plus
Yes, sir. Which one?
SCGS, right?
Yes, sir.
Just let me make sure if I got it correctly. Otherwise, my calculation will be bad. So this will be your, yes. So this will be how it is. So now your V out by V in will be multiplication of this GM Gsig divide by GDS plus GD plus SC2, and you will have Gsig plus S common C1 plus CGS. So let us take C2 common. So I will have GM Gsig divide by, in this case I will have C2 times, then again I take C1 plus CGS common outside. So I will have what? S plus GDS plus GD over C2. In another case, I will have S plus G sig over C1 plus CGS. Have you understood till this much?
Yes, sir.
Okay. The reason what I am doing this is to, now I want to draw my gain versus bandwidth plot. Okay. So this is my omega and this is my V out by V in. So at zero frequency, what is my, what will be my S at zero frequency? S is zero because S is nothing but j omega. So I will put S zero. Then what do I have at DC?
GM GMGS by C2 C1 DG.
This I will have, right? I get
Yes.
back my DC gain. You see, because my S will be zero, this will be zero, this will get cancelled, this will get cancelled, this will get cancelled. So I will have GM by GDS plus GD.
Yes, sir.
Okay. Then I will encounter, so this is let's say pole 1 and this is let's say pole 2. So I will encounter one pole and then after some time I do not know if my P2 and P1 is higher or lower. So this is the slope is minus 20 dB per decade and this is here minus 40 dB per
Right.
decade. Okay. So in this case, if you compute, so P1 will be what? P1 will be your 1 over 2 omega, or in other words 2 pi times your GDS plus GD over C2. Remember this 2 pi term, okay? So if,
Yes, sir.
and your P2 will be 2 pi times G sig over C1 plus CGS. So if you calculate this, you will find out that this is around 14 megahertz. This all the information are given in the question, right? Everything is given in the question. RD, R6, CGD, CGS, gain you have calculated, and you will find out that this value is coming around your 300 megahertz. Okay, so this is around your 300 megahertz, and this will come around your 14 megahertz. Okay. So now if I tell you what is the value of gain at this pole, it will be 3 dB lesser, right?
Yes, sir.
So what is your bandwidth now? Your bandwidth is this
14
much.
megahertz.
So your bandwidth is your around 14 megahertz. And what is your FL is in this case? FL is 0 and FH is your 14 megahertz. Why FL is 0? Because at DC also I am having some gain, right?
Yes, sir.
Now the question is, in this analysis, this is a common source amplifier. But
Yes,
in
sir.
common source amplifier, I generally used to get this kind of characteristics. The where the gain bandwidth product is this kind of one up, then flat, then down. What I am getting now? Flat portion, down, and then further down. So where is the difference? The difference lies in the fact that this pole comes from the coupling capacitances. These coupling capacitances are this one and this one. So in our analysis, in our question, it was not given. You see, the signal is directly applied. No coupling capacitance was there. So the tapering of Bode plot in this region, the tapering of Bode plot has not ever happened. Okay. So that
Yes,
is
sir.
why my FL is much lower than FH. If you see the solution handout given for this problem in your assignment, you can see that one statement is written, FH is much greater than FL. So the reason is this one, that your FL is almost equal to 0, because at 0 you are getting a gain.
Yes, sir.
Okay. So this is how you analyze this kind of problem. So believe me, if you have understood this analysis the way I have done in your higher order courses, this way only professors are going to teach you, that this kind of OTA they will make, they will keep these things, and you will have to calculate the transfer functions, and you will have to calculate the poles of the Bode plot. Okay.
Okay.
I can, if time permits, in summary session at the 13th week, I will give you how to, just by looking at the circuit, how to tell the poles, okay, or zeros if present in the circuit. I can easily see, right? Here I have an equivalent RC circuit at the output side. I have an equivalent RC circuit at the input side. So I can easily tell that there has been two poles. The two poles will be, one is the equivalent capacitance of this multiplied by the RC. Same thing is happening here, right? You see that your this pole one is what? Two capacitances, and then multiplied by G sig is nothing but 1 over R sig, right? RC, that is a time constant, tau, that is the pole. 1 over tau is your pole. Similarly, in this case also, two resistance in parallel, and then one capacitance, 1 over RC. Same stuff, 1 over tau is your pole location. Okay.
Yes, sir.
So I think that has been too much for today. So go through if you have not understood, go through the analysis again in the recorded lecture. Okay. So let's close the session here.